Okay, on the back side of that sheet, we're going to have you write in some notes. And some of you already have these notes, but this is something that is good just to review. And we'll have you just write it in, and then when you get this back, you can look it over. We have a quiz or test. We have 3 of the 4 definitions for energy. We got 4 energies listed there. Potential energy, they're not in that same order, but potential energy is energy that's stored up, like this computer. If I unplug it, which is unplugged right now, it's running off of electricity of the battery that has been charged up, and it's using its potential energy. Eventually it's going to run out if I don't plug it in and recharge it. So potential energy is energy that's stored up. Talk about water in a reservoir that would have to run through a dam, which would have hydroelectric turbines to make electricity. We go up to fishing, and we do recreation up in Yankton, and that's Lewis and Clark Dam on the Missouri. You ever been up to Yankton? I think that's the last one on the Missouri to where it's dammed up before it comes down by Omaha, down by Nebraska City and that way. Okay, but in South Dakota they probably have about 4 or 5 dams that will be reservoirs for recreational area. South Dakota is a really neat state. Some of you have been up there. Not very populated. But they have a lot of kind of neat recreation. I think a lot more than what Nebraska would have along those lines. Okay? But that's a potential energy. Okay? The sun's a potential energy. The sun is putting out energy, and some of you guys' calculators using the sun and its potential energy to charge and to access your calculator. So. Now, kinetic energy usually happens because of potential energy. And so if we go get in our car after school's out, we get out there and we start it up. The starter starts to move, the crank, and what's being used there is the battery. Is getting it to crank so that it can start the engine. Now, when the engine starts, we got that potential energy of the gas. The gas goes in the chambers where it's ignited. And when it's ignited, then those molecules move faster. We get a mini explosion that will cause those pistons to go up and down, okay, at different sequences. And so it's creating that kinetic energy from potential energy. So energy is a huge topic in all sciences because we have energy transfer. So that, anytime you have increased in motion, you have increased kinetic energy. But any motion is kinetic energy. Okay? Chemical energy is what we're studying this chapter, and we're looking at fossil fuels for the most part. And it's chemical energy that's stored up in a compound. Okay? So all compounds can have energy stored up in them. That's a possibility. Okay? The only thing that's not on there is thermal energy. I want to give you some information about the reaction that we did on last Tuesday. And this is notes that you should have down already. But you're taking methane, CH4, burning it with oxygen, you're making 2 products. Okay? And this is a energy diagram right here. Potential energy diagram. So the potential energy of the reactants is greater than the products. Greater. So that means that if the left side, which is reactants, has more energy than the products on the right side, where did that energy go? Because we have less energy after the reaction than before we had the reaction. Where did it go? Because energy is always going to be conserved. So any ideas? You guys that did the lab, what happened? This is when you guys can answer. What happened?
The water inside the can got hot.
Yeah. Where did the energy go? It went in to heat the can. So, or the water in the can. And the can itself. So that water in that can, we could use to, make hot chocolate or to, or to make warm water so that when we're washing our hands, we got warm water that makes things easier to wash up and those type of things. That's what it's like a mini water heater. That's what it is. Okay? So that energy is not lost, right? It just goes into heating up the water molecules. Okay? Does it heat up the can? Yeah. Does it heat up the air before it gets to the can and water? What do you think? Yeah, it does. Okay? So not all the heat's going into the water, right? Most of it is, but not all of it's going to. So when we have a loss of energy, that's what happens. We have something that will gain that energy. Okay? Any questions or thoughts on that? Right. This is a different way of looking at that. See, each one of these is a single bond, and they have to be broken. And when they're broken, that means bonds breaking. Anytime you break bonds, it takes energy. Anytime you take atoms apart, it takes energy. Guess what? Anytime you form bonds, you get energy out. So what happened is it took energy to break the bonds, which was that first potential energy going up the hill, and then going down the hill is reforming the bonds, and then we get energy out. So thermal energy produces heat energy. Okay? So thermal energy is heat energy. So that's your last one on there. Okay? So make sure you write that on there. All right, so we're talking about endothermic and exothermic. Endothermic, you got to put energy in. Exothermic, you get energy out. You start your car, you got to put energy in. Once it gets started, then it's a kind of a spontaneous reaction until you shut it off and you don't have sparks anymore, creating combustion. You don't have to write this part down if you don't want to. We'll continue to talk about it, but I'm going to put it up here. You're going to do four more sources of transfer of energy. This is something new we got this year. I think it's pretty neat. It's just if you were a poorer school and did not have the setup like we have, where you have the methane that we can use, okay, out of the jets, then we would use something like this, and this is filled with ethanol. And when you tip it, it's sealed, and there's a little hole here that you'll need to prime. So you want to tip it, kind of prime that little hole before you use it. And then you light it, and what happens is it'll produce a flame when you light it. Okay? There's just ethanol in there. So you guys will use that in which to do the lab. This is used to be a kerosene lamp, but I kind of adapted it so you guys can use the heat directly instead of a lamp for light. The only thing to be careful on this, if you would turn to the right to bring up the mantle, and then you would turn to the left to lower it. If you lower it too much, then this little wheel apparatus won't catch it, and it'll stay down there, and then I'll have to take it apart and pull it back up so that it will catch. So don't move it down too far, because then I have to take it apart and reassemble it, and it's a pain. So that's kerosene. You're going to use kerosene. Candle is another. Taking a look at a way of transferring heat would be a candle. And that's also, we know wax comes from crude oil. And then, then we've got sterno. Now sterno is not the chemical name for it, but it's kind of like a brand name. Yeah, it's kind of like a brand name. So we're going to just call it sterno. So if you guys want to write those down, you don't have to write them down in any order. On the other side of the sheet, you can write ethanol. I'll go ahead and write them up on the board. That way you guys can just write them. That makes sense? We put in X amount of potential energy or energy to get the reaction to go, and we're not getting any energy out. Okay? So that would be endothermic. Okay, we'll show you an exothermic. I already did show you an exothermic, but I'll show you an exothermic where it doesn't have all the reactants and products specific to it. Okay? If the bond forming, meaning bonds coming together on the product side, is greater than it takes to break the bonds, then the reaction's exothermic. Okay? So if you want to see an exothermic diagram, energy diagram, it looks like that. Same thing, but the starting point is higher than the ending point. And so we have a transfer of energy. The examples and equations we'll do later. I've given you one example, but we'll do those later. If you wrote that example down for methane, we can do that later. Okay? Any questions? This is all would be in the reading if we had time to go through it and do it. Okay? Right, before you get going, I'm going to take about 5 minutes and have you do a calculation for me. And before you do the calculation, I need you to look at this before you write anything down. I want to talk to you about it, and then you can write it down. Okay? How are we going to calculate energy that's given up by a particular heat source? I mean, how do you measure thermal energy? Okay? How do you measure it? There is a specific way we can measure how much energy is gained or lost. Now, there's this thing that some of you are concerned with, some of you won't be concerned with for years and years to come. And there's this idea called a calorie. You know what a calorie is? You know what a calorie is? What is a calorie?
How long when you burn it, how long it lasts.
Okay. So we could actually measure calories if we burn something, but I mean, when we every day when we're around, where do we see calories? Food labels. Okay. How many calories in a Big Mac? Anybody know? 2 million.
Heart attack.
Heart attack. Yeah. Do you know? Does anybody know any that works at a fast food place and know calories of a certain food? What do you know? What's that? What? Now what is it?
A large chocolate
A large. So go get a large chocolate extreme blizzard.
And we can burn it forever.
Yeah. How many calories?
like
About 1,500?
Yeah.
Holy cow. That is a holy cow. Okay? So that is calories, and how do they come up with those calories? You know, actually, similar to what we're doing in here. It's not much different. Okay? So, change in temperature times specific heat times mass. Okay? We're going to compare all these ways in which we measure energy in joules. And go ahead and write that down. I don't care. You don't have to tell me now, but later on we'll kind of compare them. Okay? going to show you how these three things work. Then I've got stands. We're going to use the whole lab. So I think we'll have 6 groups. Each group has their own lab station to work with.
What is it again?
It's mass. It's change in temperature times specific heat. 4.184. SH is 4.184.